Hello, everyone, and welcome to the third javaBin online meetup. Today we have a very special guest with us. We have Josh Long, who will present Reactive Spring. We are javaBin. We are the Norwegian jug. We have 8 regions in Norway, and we run monthly meetups, and we have about 3,000 community members all over the country. So if anybody has any questions about javaBin and what we do, or if anybody wants to be involved in what we are doing, just let us know. If you have any questions during the meetup, please use the comment field, and we will make sure to get those answered in the end, or if Josh wants it while we are throughout the session. So my name is Dervish. And now I will hand over the word to Josh, and I wish you a nice evening, and then I will see you after the session. So Josh.
Hi, thank you so much. First of all, are you recording it? If so,
yes.
Please feel free. Second of all, thank you so much, everybody, for being here. I know that there's a lot of places you could be using your energy and your time, and I know that it's a choice to be here with us tonight, and I appreciate that. And also thank you to the javaBin and to the people that work there for inviting me and for having me. I really appreciate it. Obviously, I'm very grateful to be here. I know there's a lot of much more palatable people that you could have invited, and you chose me, and I feel very grateful. We don't have a lot of time. It's all, after all, what is it now? 6 o'clock there, 7 o'clock in Norway. What do we think? It's probably getting on, right?
Yeah, it's 6 o'clock.
6 o'clock. Okay, 1800. So that's good. So we don't have a lot of time, so I'm gonna go as quick as I can, and I'll answer questions. There's usually about a halfway mark. Usually when I do this talk, it's about 2 hours. So I'll get it done in about 2 hours or less. You want my camera? Camera. Can you see that? Okay, good. Okay, good to see you. So I'm gonna share my screen right now. Give me 1 second here. Can you see my screen? Is my screen visible?
No.
Awkward. Share screen, take 2. Et voila. Is that better?
Yes.
Seems better. Good stuff. Okay, so good stuff. So good morning from sunny San Francisco in the San Francisco Bay Area. Obviously, I am having my morning just as you are entering your evening. I know that, like I said, I know that we don't have a lot of time, so let's get to it. Whenever I do a presentation, whenever I talk to people, the first thing I encourage them to keep in mind is that my code is available online for them to consider. So there it is. It's github.com, Josh Long, Reactive-Revolution. Second of all, should you have questions, while we've only got a few hours of time together, not in person, but while we've only got a few hours of time together live directly right now, don't hesitate to send me questions afterwards. I'm going to do my level-headed best to answer those questions for the next couple of hours. But again, even after that time has been exceeded, you can please send me questions, comments, feedback, whatever. I'm very happy to help you on your journey. If you have questions, please use Twitter. My direct messages are wide open. I'm there for you at StarbucksMan, or should you like, you can use email. And I'm not a big fan of email, but I've had to soften my position on email in light of Slack. You see, I I'm not a big fan of Slack. It's taken a long time to sort of prioritize Twitter, email, and then Slack. But things are getting better, friends. Things are getting better. Last year I bought one of those newfangled MacBook Pro 2019 with 64 gigs of RAM, which is, as you may or may not know or appreciate, is now enough to run both Slack and Chrome. So that's a big deal for me. I was very excited about that. I can do both now, so it's starting to become a little bit more appetizing, a little bit more palatable. That said, Twitter's still my favorite. Email's definitely my second favorite. A little bit about myself. My name is Josh Long. I work on the Spring team. I've been there since 2010. So yay, for a decade. And I work as a Spring developer advocate there. And as part of what I do, I've got training videos on Safari. I got a book called Cloud Native Java. I got training videos on Safari. I've got a book called Cloud Native Java, which is available in a number of different languages. I don't know if it's available in Norwegian, but statistically, I know most of you probably speak better English than I do, so I'm sure you'll be able to pick one of these flavors and be just fine. I have a podcast I put out every Friday. It's called A Beautiful Podcast. It's just me talking to people that are smarter than I am, which is mind you, it's a low bar, but nonetheless, lots of interesting people that I have conversations with about Spring and the ambient ecosystem. And I even had our very own Raphael Winterfeld on the show just a few short months ago. And every Tuesday, that's today, for those of you not keeping track, it's sometime on Tuesday. It doesn't matter whose Tuesday. It could be my Tuesday, it could be your Tuesday. It's Tuesday for somebody. I produce a blog called This Week in Spring, and that blog is just a roundup of all the latest and greatest that's fit to print in the Spring ecosystem. I have a video series that I do on YouTube, spring.io/videos, the YouTube channel, but there's a playlist there. It's called the Spring Tips playlist, and you can find the coordinates for that, the bit.ly URL there. And there's just me at the keyboard exploring random parts of the ecosystem, right? So just different parts of the ecosystem, in depth, right? Today's talk, the thing I'm going to do with you today is more of a breadth first discussion. I don't have a lot of time to look at any one particular thing in detail, but that's okay, because my goal, my hope, is that given how intelligent all of you are and how entrepreneuring all of you are, I know that if we broach the possibilities, you can then pursue it at your own leisure, your own discretion later on. And I also have a new book on which I'm working called Reactive Spring, and this book is now available. You can buy it now. You can even start reading it now. It's just not yet done. I would say there's another 3 chapters to finish before it's done. But it's what is there is pretty solid, so you can already start reading and feeding back to me. So if you have feedback or comments or whatever, I'm very happy to receive all that. Now, this is also the subject of today's discussion. So perhaps you don't need to buy the book after all. Hold on, let me take some coffee here. That's good. So what we're going to talk about today in our brief time together is this idea of Reactive Spring and the possibilities therein. Now, Reactive Spring is really it's not a particular technology. It's an approach to building software with Spring and a set of APIs that you can use with Spring that builds upon reactive programming. And this is, I think, really the more interesting bit of today's discussion. It's the thing that's most worthy of discussion. And it's not, if we're honest, it's not a very new thing. It's not a new thing at all. Reactive programming is a fairly old answer to a much older problem, namely, how do I scale? More specifically, how do I handle more users? How do I handle more capacity? Given the same number of computers, how do I handle more users? And this has been a problem that has bedeviled many engineers, many operations teams for many years, especially with the JVM. With the JVM, a lot of times, if you look at software written in the traditional approach, you log into those different machines and you look, and you can see that most systems today are fairly idle. There's a lot of time being spent in these computers waiting for something to happen. So we're not able to handle more traffic, and yet the CPU is not very busy at all. This problem has gone down a little bit thanks to much more efficient bin packers like Kubernetes, but nonetheless, we still have this problem, right? The number of the amount of RAM that we've got, given the And given the number of resources that we got on that computer, we're not doing as much as we could. We're under leveraged, basically. So this is a bit of a problem. And the question, of course, for a lot of people is, where does this problem, originate? Where does it? Why do we have this problem? What is the bottleneck that stops us from being able to scale up and handle more capacity, more users? And again, it's not hard to understand the motivations for this increased demand, right? Especially in the last 12 plus odd years, 13 odd years or so. We have the rise of the iPhone and the Android device ecosystem, right? So every mobile client is now a client that has to talk to your services, and that moves an increasing surface area, increasingly growing surface area of APIs, or application functionality rather, into APIs. So we have more and more things that are being conducted over the network. So we have more traffic. It's not just users requesting an HTML page and then getting the entire view and then clicking on a button and re-rendering that one post at the speed of a button click. Now it's constant back and forth communication between the client and the service that drives our demand up. So we look at these computers today, we look at the computers, and we see that if they're using these older sort of approaches to building software, as supported by Spring, for example, Spring's been around for a long time and supported by other different abstractions as well. You see that these applications aren't they're not taking as much they're not taking as much advantage of the runtime as possible. And the question is, where is the bottleneck? Well, on a traditional application, that bottleneck tends to be the threads. It tends to be the number of threads on the machine, on the computer. You see, most JVMs make it very expensive. They make it very difficult to create new threads. This is part one of the problem. Threading is expensive. And so what we need is some way to make better use of threads. There's a lot of reasons why threads are so expensive, but suffice it to say, there's bookkeeping that has to be done by the operating system and by the JVM to create each new thread. And so threads are expensive. They're not something you can create in perpetuity, and they require that you be efficient. You have to be more mindful of reusing threads efficiently. That's part one. Part two is that threads are an illusion. Remember that beyond a certain number of threads, beyond the number of cores that you have in your machine, you don't really have true concurrency, right? You have the illusion of concurrency, and at some point you're going to pay a tax by adding more threads. If you exceed the number of cores, at some point beyond that number, you're going to start paying a tax, which is to say the cost of context switching. How much time does the CPU end up doing moving work on and off the CPU just to be able to give you the illusion of concurrency? So paradoxically, adding a lot more threads doesn't give you a lot more performance, even if you were able to have a lot more threads, right? That you're not going to likely reach that latter limit before you reach the first one, but nonetheless, it's a concern. And we really do need more threads. We do need to be able to handle more concurrency because we have more traffic and we're working with more things right across the network. So the more things we have talking to each other, the more activity that we have happening, the more the need for concurrency. And this gets us to the next problem, which is even if we had much better efficiencies here, we still don't have a programming model that supports the kind of concurrent and network-bound kind of interactions that we're now seeing, right? The traditional approach to doing input and output as based on Java IO input stream is fragile, okay? So Java IO input stream is really where a lot of the problems here begin. First of all, Java IO input stream is a blocking API. When I say that, I mean, from the perspective of the thread that's running the code, that's doing the reading, you can do nothing besides block. You can do nothing besides wait when you call input stream.read. The client can't go forward, it can't do anything until that read operation either times out or completes. And either way, that's probably going to be a lot longer than you hoped it would be. So this is where we get into that inefficiency that I was talking about earlier, where you see idle CPUs just waiting for stuff that isn't happening yet. That's the first problem. The second problem is that API does not give you any control over what to do should something fail, right? What happens if I make a call to a network service that isn't there? What happens if I call a service that's taking a lot longer than I needed to? Or what if I make a call to a service that's going to return way more data than I expected? There's not really a lot of control over there. You just kind of have to know, you just kind of have to hope it's going to work. So what we want is a couple things. We want an API that will allow me to ask for data, but then jump off the thread while we wait for that data. Okay, and then we also want an API that will give us some ability to respond gracefully in the case of too much data, or to handle that lack of data, more gracefully. Okay, so we're lacking both of these in the traditional approach to building software on the JVM. There is some hope on the horizon. Obviously, Project Loom looms over us, right? Forgive the pun, and that promises the arrival of green threads, which will make threads a lot cheaper. It does so by basically building a runtime, a scheduler on the JVM itself, which is sort of like what Go does, right? Golang has the same basic mechanism where they built their own scheduler in software. And hopefully, if we change enough software, hopefully that'll just mean that a lot of us can just get free scalability. That's part one. That sort of addresses part one. Obviously, that's not a real solution for most of us for at least another few years. But hopefully, knock on wood, that'll be a thing we can rely on. But in the meantime, that still doesn't solve the second problem, which is we need a better programming model. We need a better way of expressing cooperation between individual nodes and individual actors in a system. And for this, and the efficiency problem, I want to talk to you about reactive programming. Now, reactive programming addresses this by providing a component model that supports this new inverted style of interaction. Rather than us pulling data from an input stream and waiting for that data to arrive, we are instead asking for the data and then having it pushed to us. It's an inverted. Instead of pulling, we're now having the data pushed to us, and this gives us the ability to process the data if and when it's available and no sooner. This allows other things in the operating system to happen, and other processes in the JVM to reuse those threads to be better efficient. So, sounds like a good idea. In the concrete terms, it's supported through the use of something called the Reactive Streams specification. The Reactive Streams specification are a set of common ground interfaces, 4 very simple interfaces that were defined by the Spring team at Pivotal at the time, but now we're at VMware. The RxJava team over at Netflix, the Akka Streams team over at Lightbin, but they're now called over at TypeSafe, but they're now called Lightbin, and of course the Vertex team over at the Eclipse Foundation. So all these different teams got together and we extracted out these 4 common ground interfaces. These interfaces give us a way to describe asynchronous, potentially latent, potentially unbounded streams of data. Super useful thing to have, but they are foundational. Think of them as sort of like discontiguous Java arrays. They're very, very simple, and they're not exactly the abstraction with which I expect most of us will want to work on a daily basis. So on top of that, we have Project Reactor from Pivotal and the other projects that I just described to you. Project Reactor is a way of composing and consuming reactive streams. It too is useful, but not enough. I would argue that we're not quite to a place where most of us are going to be productive. What we need is something that can help us build, in terms of these reactive APIs, something that can help us build software that we can ship into production to address the daily bread and butter use cases that most of us have. So I want to build web services. I want to talk to data stores and so on. And so for this, we have Spring. Starting in 2017, we released this first reactive version of Spring framework, supporting the reactive streams and introducing a brand new, net new reactive web runtime called Spring WebFlux. On top of which, we have since released Spring Boot 2.0 and Spring Data K and Spring Security 5 and Spring Cloud Finchley and a number of other portfolio projects that all incorporate, wherever possible, reactive streams. Now, that was several years ago. That was 3 years ago, and almost 3 years ago in some cases, and counting. So we have moved a long way since then. In the interval, we've introduced a lot of other support there, going beyond that. Okay, and in the intervening years, we've introduced new things that are not analogous to existing things. It's no longer just about achieving parity. We're now in a place where we're actually able to do things that we couldn't do before in the old way, that are native to reactive, that are reactive first. Okay, so we're going to talk about that journey, my friends. We're going to see how these things play together. We're going to build some software together today, and of course, we're going to do that by going to my second favorite place on the internet. Obviously, my first favorite place on the internet is production. I love production. You should love production. you should go there as early and often as possible. Bring the kids, bring the family. The weather's amazing. It's the happiest place on earth. It is better than Disneyland. But if you have not already been to production, you can begin your journey here at start.spring.io. Now, I'm going to build a Maven project. I'm going to use 2.30 M4. I'm going to use Java, although I suspect I might just switch to Kotlin later on. And I'm going to use the latest and greatest version of 2.30 M4 for a couple of reasons. Because I can, hashtag YOLO, first of all. And then second of all, I'm going to do so because there's a lot of interesting features in here that I don't have a lot of time to demonstrate today, but which I want to encourage you to try. So the first of which is there's now support for building Docker images based on these applications. So you can use the Spring Boot Docker support. So Phil Webb. Okay, here's the release announcement for this new feature. Basically, you just use the Maven build plugin here, and you can say where'd it go? Where's the there you go, spring-boot build-image. Okay, and it'll create a Docker image. There's also support for layered file systems and so on. That's the first feature. The other thing that's worth considering in terms of Spring Boot 2.3x is the just announced Spring Growl feature. Okay, so I've done a Spring Tips video on this, but we just announced this just a few weeks ago. We actually announced it last year, but we made a huge step forward just a few weeks ago, and I even did a Spring Tips video on this. It's a native image builder feature. So I don't have time to demonstrate this because if you know about Growl, and in particular if you know about the native image builder in Growl VM, then you know that it takes a really long time to compile anything. So I'm not going to sit here and waste 10 minutes on a traditional Tomcat and Spring Data JPA based example. That said, a lot of cool stuff there. So I've got a Spring Growl native image feature example using reactive APIs. And here's what that looks like, friends. Here's what it looks like. This is the only time I'm gonna do something with a rabbit up my sleeve, okay? So if we do Maven clean spring-boot, and by the way, there's a tax that I'm paying by running Zoom. The very act of running Zoom slows down my machine. So keep that in mind when you look at my output numbers here. Okay, good, up and running. Okay, 1.6 seconds. This is usually closer to 1 second. I wonder if I can get it just by, let's see, Maven clean spring-run, try that again. It seems to vary even with Zoom on. Nonetheless, not as fast as a native image, okay? So I've got that application. Now, I can use the Growl feature. And the way that the Growl feature works is Growl is a runtime. By default, Growl is a C1 sort of JIT replacement. You can use it like that if you want. But there's a component inside of Growl called Native Image Builder. And it does one thing and one thing in particular. If you can teach it about all the places where your application may dynamically load classes, resources, things like that, anytime where it does anything dynamic, that is to say, anytime where you introduce a class into the application that wasn't there at compile time, if you can teach it about all those occasions up front so that it's not surprised by anything you do at runtime, then it can generate a native image for you. It can actually assume that it has a closed world, and because it has a closed world, it knows exactly what's going to happen, and so it can compile code in such a way that it's actually a native image. And so that process is aided by several different things. It needs as much help as you can give it. So one thing that you can do is to run your application as a regular JVM-based application and allow it to run an agent that then monitors for all the dynamic use at runtime, and then dump out configuration files for you in that run. That's one way of capturing that dynamic information. Another thing you can do is to use what's called a feature. A feature is a program that we or somebody else can write that plugs into your Growl compiler, that gives the Growl compiler information dynamically. So we have a Growl feature that gives Growl a notion or a sense of what Spring applications do in general and what to look for. So these things, when combined, provide a lot of the information that you're going to need. And there's even some handcrafted configuration you might have to do on occasion. But here's what I did to get this to work. built it, you know, hashtag YOLO, tests are for people with regrets, haha, just kidding. And then I made a directory here that source main resources meta-inf, and then I ran the application just once. This would of course be your CI environment. I'm just running it here locally, but you'd run your application, you'd exercise all the different endpoints, you'd make sure that you hit every single possible endpoint, and that information would then be dumped out into a bunch of configuration in the directory that you specify. In this case, source main resources meta-inf native-image. Once you've done that, then you recompile with a Growl profile, and that activates the Growl plugin, which I've configured in my Maven build. And once I have that, well, I can then go to target, and there, oh, I don't have it. Do I have it? So we're gonna actually have to do this. I'll do cd target. Nothing there. So we go back, do build. Well, this one will take about 3 minutes. I'll just kick it off and we'll resume it in a minute. So you can see it's actually doing the build, and there it dumped out the dumping out the oh, I don't have the right SDK. So SDK list Java, SDK use Java, and you here we're going to use Growl VM R8. Okay. Okay, and then we do build again. Fun. Okay, so the application's up and running. Localhost reservations, good stuff. Alrighty. Control C that. It'll dump out the config. And now it's going to get to the business of actually compiling the application, and this will take a long time. So we'll come back to it in several minutes. But nonetheless, I like Spring Boot 2.3. There are a lot of cool features here. I would definitely check it out. It's definitely becoming, it's definitely becoming more aware of production. It's always, Spring Boot has always been about production. So it's nice to see these features land in the release. So while that's happening, I'm going to use at the very least the latest and greatest version of the long-term version of Java. Obviously, before me, I have 3 different choices: 14, 11, and 8. Of these, my friends, only 2 are really actually choices. The other one is not a choice; it's a non-choice. 14 is the current supported version of Java. 11 is the current long-term supported version of Java. Either one is an acceptable choice. Obviously, if you had to choose, I suspect most of us would choose Java 11. If you can, choose Java 14. Do not, under any circumstances, choose Java 8. I just did because of Growl, but do not choose Java 8 if you can avoid it, right? Java 8 is a non-choice. It's old, it's aged, it's past its prime, it's stinky, it's no longer fresh. I wouldn't use that if I could avoid it. It's technically and morally inferior. It's technically inferior because it has less features, less syntax, less performance, less runtime efficiencies, etc. But it's also morally inferior. Imagine, my friends, that the look of disappointment in your kids' eyes if you told them that you're still using Java 8 in production. Are you prepared to have that very awkward discussion with them? I don't think you are. I think, my friends, you know that you need to use the latest and greatest version of Java. It's the right thing to do. So we're going to use at least Java 11. I'm going to build an application. I'm just going to call this service because I'm really good at naming things. And then we're going to build in a number of different dependencies. We're going to use the Spring Reactive Web Support. We're going to use R2DBC. We're going to use PostgreSQL. We're going to use Lombok to make Java just a little bit more like any other language ever. Okay, so to have a little bit more conciseness in certain cases. I'm going to use the MongoDB support, the reactive MongoDB support, and I'm going to use RSocket. Now these selections are, I think, sufficient for the meantime. So I'm going to go ahead and hit generate, command enter in my setup here. Oh, it's about to finish. Oh, it's exciting. Let's go to another shell here, and cd downloads UO. Okay. And that's going to open this up in my IDE. And again, it doesn't all that much matter what IDE you use. Anything will work just fine as long as you're able to edit Java 11 code, and if you can support Maven and or Gradle. Okay, so that's opening up. Here we go. IntelliJ wants to warn me about Java 15. And I've told it not to bother me again. And you know what it does every single time I start up? It bothers me again. Okay. All right, good stuff. So that built as well. So now go to the target directory here, and there's my new build, com example reactive application. And good. So it's asking me if I want to allow Java. Yes, I do. Where did we see? There you go. It started up in 0.099 seconds. So that's a reactive application that talks to a SQL data store using R2DBC, and it talks to and it has an HTTP endpoint and then so on. You can see the data here. It's using H2, the in-memory data store, but you can talk to Postgres or whatever. And of course, if I go to the browser, localhost reservations, and there we go. All right. So now I've got a reactive application that starts up lickety-split, super fast. And let's see, allow that. And it takes much less RAM. So at runtime, those will take tens of megabytes of RAM as opposed to hundreds, like any JVM application would otherwise do. So really compelling if you're really keen on getting the most efficiency out of your production environment. This might be worth consideration. And it's made possible by Spring Boot 2.3. Okay, so there you go. That's something I wouldn't normally have time to show in a normal demo, but because we're online, because we're all kind of huddled behind our respective desks and we have access to coffee and a nice comfy couch, hopefully, shouldn't be a big deal. Now, let's look at our application. Let's build an application here. I'm going to make the font a little bit larger here, my friends. I'm sorry about that. So font, okay, 18, let's say 2020, okay? There you go. So we're going to build an application that writes data to the database. I'm going to do so in terms of my Spring Data MongoDB abstraction. So I'm going to comment out the bits that I don't need. So I don't need the Postgres dependency there. I don't need this. I'm going to comment that out. But I'm going to first bundle it. I'm going to co-locate it with Spring Data R2DBC. And once I've done that, I can build a class reservation, private string ID, private string name, and it'll be a object that maps to a MongoDB document. So in MongoDB, a document is a single record of a collection, which is more or less like a table in a SQL data store, okay? So I'm mapping this Java object to the aforementioned document. Obviously, this is a Java object, so I need getters and setters and toString, and I could certainly just do this and do that and equals and hash code, and then I'm done, right? This hideous, horrific code notwithstanding, I'm done. I could do that, or I could use case classes in Scala or data classes in Kotlin, or in Java 14, I can use records. But for now, since I'm using Java the old, I'm going to use Lombok. And Lombok was a compile time annotation processor. It'll synthesize the getters and the setters and so on. So with that in place, I can now write code that talks to that data store, but I need actually something to handle the tedious, soul annihilatingly boring read, write, update, and delete data lifecycle. Okay, so I'm going to create a repository. Now, a repository is just a classic design pattern. The idea is very simple. I want to be able to insulate my higher level business logic from the lower level persistence demands by using a repository. This repository has a lot of the same obvious sort of lifecycle methods. So save all, find by ID, check if it exists, count, find by ID, count, delete, etc. All these I think are fairly straightforward. What may not be so obvious, at least at first, are the types. The first of which is a publisher. A publisher comes from the aforementioned Reactive Streams specification. A publisher publishes data asynchronously and out of band to a subscriber. The subscriber consumes that data when it can in the onNext method. So each time there's a new record from the publisher, the onNext method is called. When there are errors, if there are errors, ineluctably, as there are errors, the onError method is called. And finally, when the publisher is done producing data, the onComplete method is called. Now, I skipped over, or I kind of hand waved away this first and most important method, onSubscribe. This gets called right after the subscriber subscribes to the publisher. And it is in this subscription, or with this subscription, that subscribers are able to control the rate of production of the publisher. They can do so by asking the publisher to either request more data or to cancel the stream of data, okay? This is super important. The subscriber is able to ask the publisher to slow down or to provide more. It's in this way that we guarantee that our services remain stable. After all, you can't very easily overwhelm a consumer that is in control of its own rate of consumption. This is not a new idea. This is flow control. Ever since we've had one computer on the same network as another, we've had to contend with flow control. And all we've done here, the only novel thing we see here, is that we've surfaced that as a top-level construct in our Java API. Okay, so it's a concept that we can work with. These are 3 of the 4 Reactive Streams types. The 4th of which is a processor. Okay, so processor, like so. A processor is a bridge. It's a subscriber and a publisher, a producer and a consumer, a source and a sink. And that's it, my friends. If you understand those 4 types, congratulations. You're certified reactive. You can move to Silicon Valley, start a new company, raise tens of billions of dollars and blow it all on lavish parties, and then move back a failure. You're ready. You're just like the rest of us here. Okay. Now, these types are very simple. As I say, they're foundational, but they fill a very obvious hole. And they're so useful, in fact, and so foundational that they have since been incorporated into the JDK. So Java util concurrent flow dot processor dot subscription dot subscriber and dot publisher. Okay, these interfaces are method for method signature exactly the same. The only thing that's different are the package, or is the package, right? And that makes sense. Obviously, we're not going to have a separate package inside the JDK, and the fact that there's a top level type. So so it's Java util concurrent flow dot processor. Okay, but otherwise the code is interchangeable, and there are even adapters that come with the Reactive Stream specification that can allow you to interchangeably adopt a Java util concurrent flow publisher into a org Reactive Streams publisher and vice versa. So once we have those, I think we understand the basics. But like I said, what about common operations? How do you map over data? How do you flat map over data? How do you filter data? How do you operate on streams of data? And for this, we need operators. So there are 2 specializations of publisher, one of which is called a mono. A mono, if you speak Spanish, in this case, does not refer to a monkey, instead refers to a publisher that produces at most 1 value, so 0 or 1, okay? It's like a completable future, except it supports back pressure. This publisher also provides a lot of operators, just lots and lots of code that I am very grateful almost every day I do not have to maintain. It's also a lot of code that I'm grateful that I do not have to write. A flux is also a publisher, okay? And a flux is a publisher that produces 0 to n values, where n is potentially unbounded, okay? These 2 publishers are from Reactor, so Reactor core, etc., right? But they are both based on the Reactive Streams publisher type. With that knowledge in hand, let's go ahead and use this new repository to write some sample data to the database. So sample data initializer, and we're going to create a Spring Bean that launches application ready event.class public void go. Okay, and here we're going to do a at component, and I'll say at private final reservation repository, and we're going to add a constructor. We can do this the old-fashioned way, like so, or we can use lambda. Okay, so at required args constructor, and voila. Now, with this in place, I'm going to start up the application. I'll just start up the application. I'm going to write some data to the database using some of the names of the people on the Spring team. Let's go and get some of these names. Madura, she's awesome. Me, not so much. That's a legendary. Yushin, she's awesome as well. Who else is on the team? Who else do we have on the Spring team? Who else do we have on Olga? She's amazing as well. We have Stefan, legit, and Jurgen. And is that 8 yet, friends? I don't even know. 1, 2, 3, 4, 5, 6, 7. I need one more name. Dr. Sire. Okay, and that gives us a reactive stream full of names. Okay, good names. And I'm going to visit each one of these names, name, into a new reservation. Okay, and I'm going to now write these to the database. I've just mapped each name, turned it into a reservation. I've created a reactive stream of each one. This is just using in-memory, it's just a literal, but that's okay. I want to save each one of these to the database. So I could do map r and then call the repository save. But what happens if I call save? Save in turn returns a publisher. It gives me a publisher of T. So if I call save, I'm returning the publisher. And what happens with map? Well, map aggregates into a container type, in this case, another publisher, the individual discrete values that return from these lambdas, from the inner lambda there. So what I get is a publisher of reservation. That's not what I want, right? I just want a publisher. So instead of doing that, I'm going to flatten the inner publisher. I'm going to use flat map. Flat map resolves the inner publisher, the inner asynchronous thing, and gives me the outer one that I actually care about. Now I can more naturally, visit each record. I don't have to visit each record, asynchronously resolve the inner publisher, and then process the innermost one, right? It does it for me. Okay, so 2 kinds of flattening going on here. We've got flattening the curve, you stay home, wash your hands, that kind of stuff. social distancing, and flattening the map. Good kinds of flattening. So I've got now three different steps in my pipeline here. Obviously, I wouldn't tease these things apart like I just did. That was just for our edification and sort of instruction, but really it's much more natural to just write the stuff as one pipeline. That's what I like to do. Now I've got a pipeline, but as yet nothing's going to happen. If I were to run this code and let it execute up until this point, you'd see that nothing is reflected in the output. Nothing will be reflected in the database either, because I haven't actually activated it. I haven't kicked it off. I haven't launched it. Think of what I just described as a pipeline through which water will eventually flow, but which doesn't happen until we turn on the pipes, until we turn on the faucet. In order to launch that pipeline, you need to subscribe. And there are different overloads. There's one that takes a consumer here, right? There's different overloads of this method that you can use, but you do need to call it, right? So if I were to run this right now, what I would see is that I would have 8 records in the database. On the second one, I'd have 16, on the third, 24, and so on. So what I want to do is I want to actually, first of all, reset the database, like so. And then once I've deleted everything asynchronous, remember this returns a mono. Once that is asynchronously processed, once that's all been written to the database and everything, then and only then do I want to process the steps in that pipeline. And then and only then do I want to call find all. And then and only then do I want to subscribe and write out the results. Okay, so like so. Now that's the full pipeline. That's what I want to do there. Okay, I'm going to run the application. Let's see what happens. Alrighty. Whoops. Did I forget to tell Maven to synchronize itself? Okay, compile again. Okay, there you go. You can see it worked. There are the names in a different order than we put them in there, right? Obviously, there's no guarantee. In this case, it looks like a lot of them kind of landed in the same order, but there's no guarantee that that would be the case. We have the records reflected in the output there. So if I go here, Mongo db.reservation.find. Okay. There you go. So there's our record, Josh. And you can see it's reflected in the console in the output there. That's because I deleted everything in MongoDB and then I inserted a new. And each time I inserted a new record, I got a UUID for the ID. So we're using Reactive MongoDB. The Reactive MongoDB support is but one of many different Reactive Spring Data modules, including but not limited to Azure Cosmos DB, Google Cloud Firestore, and Google Cloud Spanner, Cassandra, MongoDB, Redis, Neo4j, Couchbase, and Elasticsearch. These are many, some of the many different Spring Data implementations that are natively built atop reactive implementations, reactive foundational drivers, okay? Asynchronous IO based drivers. But we also support SQL, right? So we've looked at NoSQL so far. We also support SQL. We're not using JDBC because JDBC is a blocking API, okay? So that's a non-starter. But what we have is something called R2DBC. Now, R2DBC is the reactive relational database connectivity abstraction that we originated, and which has now become a sort of a community thing that people are contributing to. And there, we already have support for, among others, Postgres. And this is the R2DBC Postgres driver, MySQL, Microsoft SQL Server, H2, SAP, and a number of others besides are all now available through R2DBC. So a lot of different options there, and more being developed all the time. Once I change my build here, Maven, re-import. Once I change my build, things are going to break in my code, obviously, because this is no longer a document, and we're no longer using a UUID. Instead, it's a auto-incrementing primary key, like so. And once I've done that, I have my renewed application. Recompile, restart. Here we go. And it fails ultimately because I need to give it a URL for my configuration for my database. That's fair. I'm connecting to a Postgres instance. So R2DBC URL, R2DBC Postgres localhost orders. And we'll give it a username, orders, and a password, orders. Okay. There we go. So with that done, you can see it's written the names out to the database. There's 185, that's mine. If I go here, PSQL, U orders, select all from reservation. Okay, and there I am, lowly 185. So now we're able to talk to a SQL data store, same reactive APIs, same non-blocking basics. Very cool. Now, a very common question at this point is, what about transactions? Suppose I had a higher order business logic concern, a more granular business logic concern. How would I support something like a transaction in the reactive world? And the origin of this question, of course, is the understanding that in most frameworks, including Spring, the traditional approach to transaction delineation and demarcation is based on thread locals, which of course don't make a lot of sense in the reactive world, right? So let's talk about that. In Spring, we have a new abstraction. It's a reactive transaction manager abstraction. And this abstraction rather, allows us to store, it allows us to describe the status of an ongoing reactive transaction. Well, and the question, of course, then is, where does that state live? Where does that storage live? It doesn't live in a thread local anymore, because that doesn't make any sense, right? A thread local is what most frameworks do to hold the state of the ongoing transaction, assuming that the transaction is bound to one single thread. If you've ever used the traditional approach to transaction demarcation in Spring or in Hibernate or whatever, or in EJB, you'll know that things get weird when you start creating new threads in the middle of your transaction. You can manually start and stop your transactions, or you can do it automatically. But if you do it automatically, you need to stay on the same thread on which you originated. Otherwise, you get consistency side effects that you don't like. And the reason that's true is because behind the scenes, ultimately, there's some code in there that has a thread local, a well-known thread local that it uses to look up the current ongoing transaction, and then either commit or roll back the work that's being done in the transaction. Thread locals are kind of like a dictionary. They're a map. You give it the key, which is the current thread ID, the current thread name, let's say, and it gives you back state associated with the current thread. It's a very, very convenient thing to use if you are using threads. But in this case, when we start a reactive pipeline, there's no guarantee that the thread on which the pipeline concludes will be the same one as the one on which it originated or which it started. So we need something that will propagate data for the life of the reactive pipeline. And in Reactor, we have built just this thing. It's called a context. Okay, so you can use the context as well. It's a general purpose mechanism, and you can just provide arbitrary keys and values, right? So A, B, etc., right? And I'm using strings here, but it could have been whatever, like that, right? Whatever, another key. So I'm just using keys and values there. That context is what underpins our support in Spring for distributed tracing, for example. So if you want to propagate a tracing context from one microservice to another, that mechanism, even in logical boundaries from one thread to another, that mechanism is based on context in the reactive support there. We don't use the context in the non-reactive support, of course, because there are other mechanisms there, but nonetheless, that's one thing we can do with it. Another is for automatic propagation of the transaction, and yet another is for propagation of an authenticated principal, a security context for an incoming request. So let's say I build a service, and I'm going to use a reservation repository, and this repository is going to I'm going to inject that here, and I'll say this.reservation repository at save all, and here I'm going to create some names. I'll say I'm going to create some names actually just as I did before. Here I'm just going to copy and paste hashtag YOLO, okay, and var x equals flux.from array, passing in the names, okay, and I'm going to save all of it like so. Okay, so this is my pipeline. Now, so far, that's pretty good, but let's actually introduce some business logic here. So here, I'm going to create a little validation loop. So for each record, I'm going to assert that r.get name dot car at 0. Now, obviously, I should be checking for null here, but let's just assume that we know it's not null by this point. Okay. So the first letter must be uppercase, right? So I'm asserting that it must be a valid uppercase name in order to be persisted into the database there. And I'm doing so after the persistence, after the write. I could do it before, but it makes more sense to put it after, right? Because I don't have a thing that's been tested yet. So I'm going to have a pipeline there. And what I want to do is I want to make sure that if I write 8 records to the database using the reservation service, either all of them get persisted or none of them do. I don't want an inconsistent state. So reservation service. Here we go. Reservation -service dot save all, and voila. Okay, there's my pipeline. So names is going to everything within the pipeline here will be persisted, either all of it or none of it, right? So it's a atomic. Everything before that, remember the delete all and the find all that happens outside of a transaction. So no matter what, I'm going to delete everything when the application starts up. I may write 8 records to the database, assuming none of them start with a lowercase letter. And then I'm going to find everything for sure, and I'm going to write it out. So let's go ahead and restart the application. Notice that I have lowercase j there. So it's lowercase j. You can see it's reflecting in the output there. It's reflecting in the output that the name must be uppercase. Localhost reservations. Oh, I don't have that endpoint. Local, well, it must be uppercase. Then we can go to the database, right? Select all from reservation. Yeah. Oh, I don't have at transactional, friends. That's what I forgot to do. So at transactional, and now take 2, hopefully, because there's a reactive transaction manager abstraction plugged in the background there by the auto configuration in Spring Boot. I have 0 records. Okay, so obviously we still see the error logged, right? It's observing, it's noting the error, but now because it's transactional, I've actually atomically committed and rolled back the behavior there. There's reactive transaction demarcation support for R2DBC, which includes all the various R2DBC implementations, as well as MongoDB and Neo4j and Google Cloud Cosmos, Azure Cosmos DB and Google Cloud Spanner. So lots of good R2BC, lots of good reactive transaction demarcation examples out there already, and more are coming all the time. Okay, so we've got 8 records in a database. We have SQL and NoSQL. And the next natural thing is, well, can I build a REST controller? And people often do this kind of stuff. So they'll use Spring MVC or something like that, and they're going to want to build an HTTP endpoint. And that's very natural to do with Spring. So here's how you would create a reactive HTTP endpoint, like so. Okay, private final reservation repository. Okay, and then required args constructor, and we're just going to say return this repository at find all. And if we restart the application, we can go to the browser here. And did I miss something here? Wrong spelling. Oh, and I still have the lowercase name. So reservations. Good. Restart. Okay. Localhost reservations. Good. So there's our data in the HTTP endpoint, and that works. That's fine, right? It's very straightforward. But this is a whole class with a constructor and fields and storage and all that kind of stuff, just to express that I want an HTTP GET endpoint for the reservations URI that returns this stuff here. So a lot of times for more, if I want to be a little bit more nimble, and I don't have a huge, I don't have a lot of correlated endpoints that are sharing common storage for things, you know, that kind of stuff. I'll use the router function style, okay, the function reactive HTTP endpoint style that was introduced in Spring Framework 5. This is a natural thing to do in a reactive application. New handler function. create a new server response .ok.body. And here, I'm going to create a reservation repository, rr.findAll, reservation.class. Okay, good stuff. So there's our reservation repository, adding the static import, and there we go. Okay, there's our reservation repository. Doing our HTTP endpoint, doing exactly the same thing, mind you, in one line of code. We've got the HTTP predicate, and then we've got the Lambda that produces the response. So it's also a builder API, so I can chain these things together if I like. I can use you know, a while loop or for loop to string these things together to decide how many of them to add, which is a lot more difficult to do with annotations, right? Unless you're Raphael, most of us are not in the business of re-engineering our classes before they get loaded, or even after they get loaded, to have new methods dynamically, right? It would be very difficult to go through a for loop and then add new methods with annotations on them so that Spring would find them when it starts up for most of us. So this is actually very convenient. I can just use a for loop and add those records there, okay? So now I've got an application, it has HTTP, it has an HTTP endpoint, it's got data in the database, and I can hear you collectively going, so what, right? Who cares? I could have written 8 records to a SQL data store that gives me a simple HTTP endpoint, you know, with 8 records in JSON. I could have done that yesterday. I didn't need the reactive stuff to do any of that today. And so the question you may be wondering is, why do I care? What does this all matter to me? Well, fair point. What I've demonstrated to you thus far, my friends, is parity. I've demonstrated to you that I can get the same kind of things done today with reactive applications as I could do before. And actually, I would argue that we can do so more efficiently, more effectively. Consider this. When you learn reactive APIs, the upfront cost of learning the reactive stream specification, learning how to write code and think in terms of these reactive APIs is, I grant you, not trivial. That said, once you've done that, you're in. Life becomes much simpler because now you have to think about one kind of stuff. You have one kind of thing in your life. That is to say, publishers. When you're not sure, use a publisher. Life becomes much simpler at this point. Instead of having to learn the Spring MVC style API for using server-side events, where you return SSE emitter and all this stuff, you just use a publisher. Do you want to learn how to do WebSockets, where you have to create a simp messaging template and all that stuff in Spring? Okay, fine. Or you can just use a publisher. What if you want to create an HTTP API that returns 8 records of JSON? Yeah, you got it. You use a publisher. What if I want to talk to Kafka? Do I have to learn the Kafka API or RabbitMQ or JMS? No, just use a publisher in this case, right? I think you're starting to see what I mean. Everything is a publisher now. And so amortize over all the different applications of that API, there's much less work to be done. So not only do you get the same concise code as you had before, if not more concise. And again, a lot of this looks fairly similar to Java 8 Streams API. So if you're comfortable with that, you're almost halfway there with the reactive APIs. Not only is the code as concise as it's ever been, but it's now more consistent, right? It's now more easy to reason about, more natural to reason about. This gives you a huge leg up on the competition, right? If you're trying to write applications, it's very nice to know that all you need to know is how to create and work with reactive streams. And you have to figure out how to plug in those reactive streams. But beyond that, things are very simple, right? So that's one big benefit here, is that not only have you done what you could have done before in roughly the same amount of code and using the same logical concepts, you know, add transactional and so on. Not only have you done that, but you've also done it with more impunity, with more room for experimentation, because you're no longer having to pay the cost of learning a new API each time. Okay, so that's part one. Part two is, now that I've got this application up and running, what can I do that benefits from reactive APIs? Where am I not just achieving parity, but where can I actually claim to have been put in a better position because of my use of reactive APIs? And here, I want to talk to you about things that require liveliness. Now, before I get too far down that road, let me make sure there are any questions. Let me see the chat here. Okay, camera. Okay, I think everybody's, if you have questions, I'm going to check in again at the end of this, just to make sure we're on the same page. Okay, my friends, so we've got now an application that's up and running. What I want to do now is I want to take advantage of the fact that I'm using reactive APIs, and where I really benefit is in the situations where I have possible liveliness concerns. That is to say, things where I might need to get the latest and greatest view of something. Think about this. If you're building a chat application, you know, the stereotypical chat application, a client connects to a service and the service pumps out updates based on the state of the chat room to the client. Well, of course, in order for the client to get the latest and greatest updates as fast and efficiently as possible, they need to stay connected. In the old world, such a connection implied 2 threads, one on the server, one on the client, being kept open because the sockets were being kept open. In the new world, the number of file descriptors, or in this case, sockets that we have, doesn't necessarily need to line up with the number of threads that we have. We can have many more file descriptors than we do threads, and that's okay. We can break that link. We can decouple one from the other. This gives us a lot of scalability. So let's build a WebSocket endpoint that demonstrates a never-ending greeting service. Oops, I got a message here. Reactive. Will Project Loom negate reactive? No, because it's all about control flow, right? So like I said, we're going to see, well, like I said, all Project Loom does is it gives you cheap threads, right? So that's part one. But I said there's 2 use cases here for reactive. One is making better use of threads so that you can repurpose them and reuse them. And then 2 is having a better programming model for building things that coordinate with each other, right? And that's what we're going to see in this next hour, okay? And I said that at the very beginning of this presentation. So let's build a greetings service. And a greeting service is going to produce a infinite stream of greetings, okay? Given a greeting request. And the request will have a name, and in response, I'll have a message. Okay, so at data, at all args constructor, at no args constructor. Ta-da. Okay. Greetings, response, greetings, request. Okay. So there we go. There's my simple service and my my payloads. Let's see what that looks like. In response to a incoming request, I'm going to create an infinite stream. I'm using an adapter here from the Java 8 Streams API that produces a new greetings response. So new greetings response, hello, request dot name at instant dot now. Okay, so this is my infinite stream, and I'll then stagger the results. So what I've done is I've used this delay elements thing to actually slow down the rate of production, because if I were to leave this code as it was, it would very quickly exceed the boundaries of my console, scroll right off the edge of my screen, down to the floor and out the door. I wouldn't be able to see the end of it. It would go so quickly. So what I want to do instead is I want to stagger the results. I'm going to slow them down just a little bit artificially by 1 second. Now, what I'm doing here is using time. I'm able to model time with my API, right? Because reactive APIs use time as a dimension of what you're doing. It's no longer just an afterthought. And the reason I can do that is because behind the scenes, the thing that moves one thread to the other, one thread, moves work onto one thread or the other, that thing is called a scheduler. And that scheduler is omnipresent. It's always there. It's just that you don't necessarily worry about it. So you say subscriber, subscribe on, and you provide a scheduler, right? From executors dot blah, blah, blah. So I can override the thread. I can override the scheduler on which a pipeline executes, but I don't normally need to do that. Behind the scenes, by default, you have a thread pool, a scheduler that has as many threads as you have cores, as I said before. And that's fine, so long as you don't monopolize any one of those threads. If you have 4 cores, which is a very common, very low level it's a very common form factor for a mid-range laptop these days. If you have 4 cores, then you only have 4 threads in a reactive application, and that's fine. Remember, so long as you don't block any of those threads. As soon as you block them, you get into trouble. So your scheduler is 1/2 thread pool, 1/2 clock. Okay, and it's very important that you never block any of the threads in that that thread pool, that scheduler, so long, especially if that scheduler is a non-blocking thread pool. Okay, very, very important. If you have a thread pool that's, or a scheduler that's been marked as non-blocking, it's very important that you don't do anything blocking on that API. If you do, what will happen is you'll end up blocking not just one user, but 25% of your users in the case of a 4-thread thread pool. Okay, it's very important that you not do that. So we've built a tool that you can use called blockhound. Blockhound is kind of like a Java agent. It's a Java agent to detect blocking calls from non-blocking threads. So you add it to the class path, you do blockhound.install, and then right before your application, you do that right before your application initializes in public static void main. And then when your application runs, if it detects anything that's blocking on a non-blocking thread pool, like thread.sleep, it'll throw a blocking operation error. Okay, so that's actually that's very convenient. Now we're able to find any cases where you're accidentally wasting memory or wasting time on a thread. Very convenient in ferreting out any blocking uses. Now, of course, you can have blocking interactions, but you just got to make sure that you subscribe on a scheduler that is meant to support creating a new thread per request, right? In the old blocking sort of fashion. You've always had the responsibility of making sure that you had properly isolated your different thread pools. That's never changed. It's the only difference now is that we are giving you the tools that make it much more easy to do this in a more granular fashion per pipeline. Okay. So there's my infinite greeting service. Now I want to create a WebSocket endpoint. Okay, so let's go down here. I suppose I can go up here. Okay. Class greeting WebSocket configuration at bean. Here, I'm gonna describe to the framework what URL to use to mount the WebSocket endpoint to the web framework. So keep in mind, WebSockets are a binary protocol, but they're a binary protocol, but they are initiated by a handshake that's done with HTTP. So I have to I'm going to tell the framework that when somebody goes to WS/greetings, we want to upgrade them to the WebSocket protocol. And that's the mapping that I've just done there. Once we've done that, we're telling it to upgrade to a particular WebSocket handler, which will actually handle the bulk of the communication, the WebSocket communication. And that's where our business logic lives. We're going to come back to that in just a second. And the last thing we need is a WebSocket handler adapter. Okay. Good. Okay, so now we have the WebSocket handler. We have a WebSocket handler adapter, and now we can actually implement the business logic. And the contract here is fairly straightforward. When the client and the server connect, they are given a new WebSocket session is established, and it's with that session that I can then start to communicate with the client. So I can say session.receive, and that gives me a publisher of WebSocket message. Okay, so I want to use this to receive any incoming names, greetings requests, and then I'm going to map each one of those WebSocket messages into text, like so. And then I'm going to map each one of those to a call to greetings service.greets. I suppose I better do this first. I'll say map txt new greetings request. Okay. Good. I'm going to use flat map here. Okay, txt. And from there, I will then map each response. So each greetings response that I get back, I'll get the message. And for that as text. And then for each one of those text messages, I'm going to create a WebSocket text message. So I'll say session.textMessage text. Okay. And that'll become the entire interaction. That's the entire chat, if you will. Okay. That interaction receives data from the client, maps each WebSocket message that's coming in into its constituent text value, turns that text into a greetings request, passes that to the greetings service, which gives us back a stream of values, which I then map over, unpacking the constituent text bits and turning each one into a text message. Okay. And I'm going to send it back to the client like so. So session.receive send chat. Okay, there's the entire application. Obviously, this can be a Lambda. My ID is telling me this. So there we go. So there's my entire thing. Okay, and really, you know, if I can, I will. Okay, so I have a WebSocket handler. Now I want to demonstrate that this works to you. I want to demonstrate how this would work. And so I need to do something that I'm not proud of, something that I feel if I had any other more expedient way to do this, I would, but I just don't know of a better way forward. So I'm afraid I'm going to do this. And again, I wouldn't do it in polite company. It's not something I'm proud of. I just don't know of a more efficient way to do this. I don't know of a more expedient way to do this. Okay, and I'm not proud. Okay, I'm not proud, but it just serves the demo flow here. I want to demonstrate the WebSocket handler there. So I'm gonna create JavaScript. Okay, so source main resources static file ws.html HTML body script window.add event listener load and event and const ws goes new WebSocket ws localhost 80 ws greetings ws.add event listener message. Okay, and on open. So when the socket first opens up the connection, when it's first live, I can then send a message to the service using the WebSocket API. So I can say hello javaBin. Okay, and finally, when the results come back, I can log out the individual records here as they arrive. Okay, so there we go. There's my semicolons. Gotta have semicolons. Okay, let's go ahead and restart and see what we got. How are ordered? I think they mean ordered queries handled. Yeah, you just use then many, right? And you can do flat map sequential. If you want to ensure that you get the results back in a particular order, you use flat map sequential. If you were talking about like you want to have a query that goes first and then another one and then another one, use then many. As I say, you can compose these things. Okay, good question. Okay, so localhost ws.html source main resources static. I feel like I did my part there. What happened? Maven, are you upset? Source main resources static. Okay, so there you go. You can see if I look at the console there and the developer tools, I can see being reflected in the output there a never-ending stream of greetings from the greeting service. It's going to produce new values forever and ever and ever and ever. It's going to go on and on and on without end. It is endless. It has no end. It is like the oceans and the skies and the stars and the bugs in your code. It's infinite, my friends, infinite. It's going to go on forever. And that's okay, because in between the raindrops, in between each new response, in between each new response, that thread is being freed up so that something else can reuse it. This allows us much better scalability. This is the real key takeaway from reactive programming. It's not that I can build services where each particular transaction is faster. And indeed, in some cases, because of context switching, they might be just that much slower, right? It's not that any one transaction is faster, it's that it can handle many, many more transactions. I'm not trying to give you benchmarking numbers, but the goal here for simple round math and simple ease of understanding is to double the number of transactions and keep the same hardware, or to divide the hardware by 2 and keep the same number of transactions. That's the goal. It's not about making any one transaction go faster. Reactive APIs gives you better scalability while letting your programming model be more consistent. So we have seen thus far what it looks like to build an application that takes advantage of the reactive APIs in the context of a monolith. Now, as we kind of we can see the finish line of our time together. We've got another 40 minutes. Now let's turn to what it looks like to build an application that takes advantage of reactive APIs in the context of microservices, okay? So let's go back to start.spring.io and build a client. And here, same as before, I use 2.30 M4, I use Java. I'm going to call this client because, again, very good at names. People say that. They say, Josh, he's great at names. Lumbuk. I'm a bit like my dad in that respect. My dad, we had a dog, and the dog was a little white poodle. So my dad named it White Dog. Not very good at that. But then we had another dog, another little white poodle that showed up after the first one died after 10 years. And so my dad, again, great with names. You can see where I get it. He called it Two, you know, TWO or TO. Either way, it worked. It was White Dog 2. My mom insists that when I was born, he wanted to name me White Boy. And I'm glad that she chose my name. So let's see. We've got Lombok, we've got Reactive Web. What else do we need? We want the Spring Cloud Gateway. We want the Resilience4j circuit breaker. We want RSocket. We want the Reactive Redis support. Redis, okay. We want Spring Security. So we've got Lombok, Reactive Web, Gateway, Resilience4j, RSocket, Spring Data, Reactive Redis, and Spring Security. I think I'm happy with those selections. I'm going to go ahead and hit generate. That gives me a client. And actually, I suppose I should have better named this. I could have better named this the edge service, okay? An edge service is just that. It's a service that lives at the logical edge of the architecture. It's the first port of call for incoming requests from the outside world. And it's a natural place. It's a natural place for us to address things like API adapters and API gateways. An API gateway is just a thing that is ignorant of the particulars of an incoming request. Pardon me. And it acts in a generic fashion, ignorant of the particulars. It doesn't care about the payload that's coming in. It just knows about headers and basic protocol awareness, right? It's great for generic cross-cutting kinds of concerns, things like routing and status checks and redirects and compression and things like that, okay? An API adapter, on the other hand, actually changes the incoming request. It might enrich it, it might transform it, usually in service to a particular client that needs a particular view of the downstream state of the downstream service, okay? So I am going to prune some dependencies that I don't need just yet here, okay? So get rid of those. And we're gonna go ahead and say Maven, re-import. And here we go, there's my application. Now, what I wanna do is I wanna build an application that acts as a gateway. And to support this use case, I can use the Reactive first Spring Cloud Gateway. Now, Spring Cloud Gateway is, you know, think of it like it's Kong ++ or Nginx ++, but it's not, it's Apogee --. So if you're looking for a really full-featured API gateway like Apogee, yeah, just use Apogee. If that's if that's the best choice for you, then you should absolutely use that. But for a lot of use cases, you'd be surprised. This could be more than enough, right? So I'll just create a simple API gateway here. And the idea behind the API gateway is that you describe routes, one or more. Each route has a specification. And the spec describes how incoming requests are matched. So here, I'm going to say that anything going to /proxy and to the host .spring.io is matched. And I'm going to say I want to route it to localhost 8080 / reservations, right? This is the downstream microservice. My microservice, the one that we're running right now, the edge service, is going to run on port 9999. So this is the incoming predicate. I've got a bunch of incoming things I can use to predicate. I can say based on the presence of a cookie or a header or a host or a path or whatever. And then assuming it matches, I'm going to forward it to this URL. But consider what's problematic with this. My path on the incoming request is proxy. The path on the outbound request is reservations. So at some point I need to modify the incoming request and set up the reservations path as being the outbound path, okay? So I'm going to use a filter here to transform the incoming request. Here I'll say set path equals reservations, in which case I don't need this. So if I had not done that, if I had left things as they were just a second ago, the URL would have been localhost 8080 / reservations / proxy, which doesn't exist. That's why it's very important that we transform the path, okay? The filters here are really where all the power is. This is where you get most of the power out of Spring Cloud Gateway. There's filters for everything. If you want to do a redirect, if you want to do a circuit breaker, modify the headers, do a retry, do also, modify the response, set the request headers, rewrite the path, preserve session headers, set the status, whatever, right? There's support here for all that kind of stuff. Lots of good stuff. Let's say I wanted to add a custom header here. So I say HTTP headers, right? HTTP headers, please. Okay, access control allow origin, that's for cores, right? So if I have an HTML5 browser-based client, I can't afford to modify every single downstream service that I want my HTML5 browser client to talk to, but I can go ahead and add that header here in the gateway. I can also do other things. I can do rate limiters, for example. Rate limiters are great for a number of different use cases. One use case is, hey, I've got an aggregate number of requests that I can allow per second in total for the entire planet, right? This is like the mainframe use case. Mainframes are notoriously very hard and expensive to scale out. Once you have reached n+1, where n is the number of requests that you can handle in one mainframe without having to buy another one, you're in trouble, because that extra request is going to cost you a new mainframe, and those are very expensive. They're not cheap at all. So you want to avoid that if at all possible. It becomes very useful to serialize requests into that mainframe, or at the very least reject anything that exceeds your budget. So that's one possible use case. Now, the other is, hey, if I have, let's say I'm using a commodity cloud provider, anything at all in the last 10+ odd years, AWS, Google Cloud, Microsoft Azure, Cloud Foundry, Heroku, Kubernetes, Cloud Foundry, whatever, anything, right? All these things will work just fine. If I'm using any of these cloud providers, then my problem today isn't scale. I can automatically scale up based on demand. What I care about instead is limiting the number of requests that any one particular user can make against my system, right? I want to ensure that everybody's playing a fair game, that nobody's exceeding the capacity of the system. So if somebody is, sending thousands of requests per second and the rest of the site is suffering because of that, then I want to stop that. So a rate limiter can also be used for that. But consider what happens with a rate limiter. A rate limiter has to keep a track of how many requests have been going through, and if it exceeds the budget that we prescribe, we need to start rejecting that count. What happens if we have more than one edge service, though, one more client, okay? If we have more than one edge service, then we need to make sure that whatever count they use, whatever budget that we prescribe is visible, right? The tally that we keep has to be visible across all the different instances of the client service, of the edge service. So we need to store our number. We need to keep an atomic number somewhere that all of the clients can see in a consistent way. I want something like an atomic number, but it needs to be stored outside of my Java application. Redis is a distributed data structure server. It's a key value store, and it's blazing fast, and it has atomic numbers. So we can use that. So we're going to use a Redis-based rate limiter. Okay. And the Redis-based rate limiter is going to provide a rate limiter. I'm going to limit the number of requests per second to 5, bursting to 7, and I'm going to configure that here. So set rate limiter. Okay, rate limiter. Now, consider that Redis is a key value store. So you need to give it a key in order for it to find the value, in this case, our atomic number. If you have the mainframe use case, then you can just say, hey, give me a key resolver, mono.just, and then give it a key, right? Like that. That's a very common thing to do, I guess. But it's kind of ignoring the opportunities here. You could look at the incoming request. Exchange here is just another way of saying request. And it also has the pointer to the thing that you can use to produce the body. So this kind of ignores the incoming request. That's a shame, right? I'd much rather take advantage of that. So what you might do is, if you want to make sure that, for example, each user is only allowed to have 5 requests per second, you can say return request dot give me the current authenticated principal dot map principal get name. So there, if I have a current authenticated principal, I get the name and I use that as the key. So JLong, for example, would be the principal. And otherwise, if the principal is not authenticated, then I just return an empty publisher, which is to say no key. Therefore, if you're not authenticated, you get nothing. Okay, very common strategy. I can replace this with a lambda. It distills very nicely as a just a simple thing like this. So here we go. Get rid of that. Get rid of this. Good. Okay, that's not so bad. It's not so bad at all. It's actually a very common thing. If I'm honest. So it's actually a very common thing. So we actually wrote it for you. You can use principal name key resolver. Okay, that's actually provided for you out of the box. Here you go. You can see it says exchange principal map switch if empty. It's actually so common that's the default. So we're back to where we started, and that will work just out of the box. So now we have a principal named key resolver in place, which implies that we need to have a principal. And here we have a discussion around Spring Security. So Spring Security is a very old framework. It's been in the Spring ecosystem for a long time. It addresses two orthogonal concerns: authentication, that is to say, it answers the question, who is making the request, and authorization, which answers the question, what may they do once they're inside the system. Authentication, we can address with a hard-coded username and password based thing here. Now, while I'm doing this, first of all, let me discourage you from ever doing the same thing. You shouldn't be using hard-coded usernames and passwords, but this is a demo, friends, so I'm going to go ahead and do that. And then second of all, let's consider what happens in certain kinds of authentication here, okay? Now, when I authenticate a user in my service, there's a lot of different ways for me to take context from the incoming request and turn that into some notion about who's making the request, okay? I could, for example, look at the filters. I could look at the tokens in the request, right? I could look at an X59 certificate in the incoming request. I could take a cookie in the incoming request. But a very common thing that people do is they use usernames and passwords. So let's suppose you're doing HTTP basic, okay? Very common thing. So that reminds me, I should enable that. So I'm going to say X. I'm going to do customizer with defaults here, but with this one, I'm going to disable it. So let's suppose I'm doing HTTP basic. Okay, so I've got HTTP basic, but I am now going to make a call to my backend bespoke username and password table. What happens there, right? I have a username and password table. I am going to look up the username and password. I'm going to say if the password matches the incoming request, great, let it go through. But hopefully I'm doing the right thing. Hopefully my passwords are encrypted, right? I want to make sure that I don't just allow any old random request to come through. So I need to make sure that my password is encrypted because I don't want passwords in my database to be in plain text. So that means I need to encrypt the incoming password as well. I need to, because it's not going to match otherwise, right? Encrypted versus non-encrypted, they're not going to match, even if they are at the core of the same string. So what do? I encrypt the incoming password. How do I do that? Well, I might use a password encoder, as is provided by Spring Security, something like bcrypt. Okay. Well, bcrypt is the default standard these days. It's what we configure by default in Spring Security, but it's pluggable. And there's other ones, and that might change. So today it's bcrypt. It might be a different password encoder tomorrow, and that's why, for example, we don't encourage you to use the default password encoder because this might change tomorrow. Today it's bcrypt, and all your passwords in your database are going to be automatically encrypted as bcrypt. But tomorrow they might be encrypted with quantum bcrypt or something like that, right? In which case this code would break. So we encourage you to be very explicit about how you've encoded the passwords in your database and which ones you expect Spring Security to use. Okay, but that's neither here nor there. Let's suppose you've got a request, the password comes in, you encrypt it. How long does that take? Well, it takes some time, right? It's computationally inefficient. It's going to sit on the CPU and encrypt that password. And when it encrypts it, it's going to sit on the CPU and block a thread. This is one of those things where you can't just rub reactive on it and make it better. There's no way to make this go faster. It's just going to take the time that it takes, such as the nature of cryptography or any kind of algorithmic intensive or algorithm intensive activity. So cryptography in general is going to be computationally inefficient. The Fibonacci series is going to be something you want to avoid as well. Running Slack, again, very, very, very expensive on the CPU. So you want to avoid this kind of stuff, right? It's gonna slow down your CPU. But you can't really get around it sometimes, right? So in this case, Spring Security doesn't have to do a lot in order to be able to accommodate reactive APIs. It just works because there's nothing we can really do, right? For a lot of the use cases, especially around usernames and passwords. But the silver lining here, as with the example earlier where I showed you that you have to run your Java application, run it through CI, the implication there was you have to test your code thoroughly to get the most coverage so that you can capture the dynamic behavior of the application and then use that to turn your application into a well-tuned growl application. So the result was you had to get your code right and working first and then make it fast, but you got them both done at the same time, right? By testing it, you also got faster code. The same is true here. This is one of those rare situations where you can make your code more efficient and more performant and make it better. So what you want to do is you want to avoid constant exchanges where you have to do password encryption. One way to do that is to use a token-based authentication mechanism, something like OAuth. OAuth exchanges long-term credentials for short-term credentials. So you exchange your username and password for a token, which can be easily revoked essentially, and which has a much shorter lifetime. That token is also cheap. It doesn't require constant encryption on every single request. So you do the encryption just once at the initiation of the session, and then every subsequent request thereafter benefits from that. Now you're spending much less time on the CPU per request. So it's the better thing to do anyway. Okay, so we've got our application. It's up and running. I hope it is. There it is. Alrighty. So curl host javabin.spring.io HTTP localhost 9999/proxy. And of course it's complaining because it's unauthorized. So -u jlong:/pw. Okay, so there's my request. You can see that as I make a request, I only have so much capacity left over. There's my JSON output, etc. Okay, so while true, do done. Okay, you can see I'm driving traffic using a while loop, and the benefit of that is that a while loop is very slow, especially in Bash. That's why I set the rate limiter to just 5 requests per second. In a normal application, you'd have a good deal many more requests than 5 requests per second. So I set it down to this. I'm saying 429 too many requests. Okay, Bash is able to drive more than 5 requests per second. That exceeds the budget. I can see it's kicking me out. It's saying I've only got zero capacity left over, and that's happening for a lot of the requests. But obviously, some are getting through, so that's okay. That's okay. That's okay. That's okay. That's okay. And it's not 429 too many requests, right? So the rate limiter is working. Spring Cloud Gateway gives us a lot of flexibility here. We looked at security, we looked at API gateways. Now let's look at API adapters, which are great for acting on the request and creating a new response that gets sent back out. So server response routes, okay? And here I'm gonna create an API adapter. I don't have a custom API for this. This is exactly one of the wheelhouses of reactive programming. This is one of the perfect use cases for reactive programming. So I'm just gonna go ahead and create a new view on the reservations data from our reservation service that returns only the names, okay? In order to do that though, I need to make an HTTP call to the downstream microservice. So I'll say HTTP, okay? And I'm gonna use the web client builder here to make that call. Good. I'll inject that builder here, web client. Okay, and my goal here is to make a call to the downstream service. I'm going to say, make an HTTP GET call to localhost 8080/reservations. And for each record that comes back, turn it into a reservation. Now, of course, I don't have the client-side representation on the class path here of a reservation. So I'm going to go back to my service and I'm going to do something terrible, something that you should never ever do, ever, not even when you're all by yourself at home and no one is looking. I'm going to copy and paste code. So let me paste that all here, and then I'll copy and paste that whole thing over to my client, my edge service here. Okay. Good. Good. Yikes. How did I let that happen? Good. Okay. So now I have my DTO. Now I can take the records in the JSON response, turn it into a reservation like so. And then for each reservation, for each result that comes back, I'm going to map the reservation into its constituent name. Okay. And that gives me a reactive stream of names. Good stuff. Now, I'm going to send that back to my client. So I say server response .ok.body names string .class and voila. Okay, that's the entire pipeline. Now, is this always going to work? let's assume I was not using a hard-coded host and port. Let's suppose I was using a discovery client abstraction, the Spring Cloud Discovery Client, which lets me connect or plug into different service registries like HashiCorp Console, Netflix's Eureka, Apache Zookeeper, etc. Let's suppose I was doing that, and I was doing smart client-side load balancing. Okay, ignore the single host and port problem. Is that still reliable code? Would you trust this code in production? I wouldn't, right? Something's going to fail. Something might happen. And if something fails, well, I want to catch and respond to the error. So I can say, okay, if something goes wrong, then I want to return a default string, right? If something goes wrong, I may want to retry. I may want to retry 10 times. I may want to retry and then do a back off, right? So retry back off. And I want to have an exponential back off. So I can say, wait a second for each attempt extra. So a lot of different things that I might do to make my code just a little bit more robust. I might also consider a timeout, right? I can say timeout. But timeouts in my mind are a really poor choice, okay? So let's suppose that, let's talk about what we do when we use timeouts. What are we trying to achieve? When we create a timeout, what we're trying to say is, hey, I want this to time out so that I have another chance to make the request. I want to attempt the call one more time. The reason I do that is so that I can get the response back for my client in time for my SLA, okay? So SLAs are really what drives the use of timeouts. And at the very minimum, you want a timeout to give you enough of a window so that you can try the attempt again, right? What else is the point? So I make a call. I make a call to the downstream service. I want to make sure that if my client expects me to provide a response in, let's say, for nice, simple math, in a very indulgent, very luxurious 20 seconds, then I need to make sure that any downstream dependency I have, in this case, on the reservation service, I need to make sure that that returns within 10 seconds so that if it fails, I can retry one more time, okay? And so maybe here, I'm going to retry one more time, okay? All right. What happens to the service that I'm contacting? What if it in turn calls another service? And so that service needs to return when? Well, it needs to return in 5 seconds, right? All right, what about the service it consumes? Well, it needs to return in 2.5 seconds, right? So it decays very quickly. It becomes very untenable. Just a few hops away from the original request, it becomes very untenable to use timeouts as a way of ensuring that we get a response in time. What I want is to respond within a certain time frame. I want to guarantee I get a result within a certain time frame. But who's to say that retrying the request to the original host and port is going to work? Perhaps if you're using client-side load balancing, it'll automatically retry the request against a different node. But even there, why bother waiting for it to fail? Why not just assume that something might fail and make the request to a number of different nodes? This is exactly the premise behind hedging, service hedging, right? Hedging is a very simple idea. You'll see people talking about it in Google, at Netflix and Uber and other companies that operate at scale. The idea behind hedging is that you want to make sure that you meet a certain deadline. And so in order to guarantee that you don't get disappointed, you make the request to more than one node, more than one discrete instance of the service on more than one discrete instance of one discrete node, okay? More than one discrete node. So if I call the reservation-service, which I can discover using the service registry, I can ask the service registry to give me the host and ports for 3 different discrete instances of the reservation service. I can then launch the same request at the same time to all 3 different nodes, or I'm using 3 as an arbitrary number, but anything will do. And I can keep the fastest response. So I can say, publisher, let's say I have a hypothetical host 1 to do, okay? Host 2, host 3, okay? So I've got 3 different calls in flight. By the way, when I have this pipeline here, remember that's not actually in flight. I've defined the template, but I haven't actually launched it because that doesn't get done until somewhere in the bowels of the body method. So I've defined the pipes, but I can rewire the pipes later on, and I'm doing that here. So let's suppose I've defined 3 different pipelines. Now I want to tell the reactive APIs to give me the fastest one first. Okay, so I can just say, give me the first one to return. This is a bit like the select function in POSIX, P-O-S-I-X. It just returns the fastest reactive stream and it applies back pressure to the other two that responded slowly. So again, that'll work just fine, assuming your services are idempotent, right? Obviously, you don't want to do this on the charge the customer credit card endpoint, right? That's not going to be great. But for things that are idempotent, this is a good strategy to guarantee that somebody responds to you within your deadline, right? If one service is out to lunch or failing or garbage collecting or whatever, that's okay. You've still got two other attempts in flight, one of which is bound to work. Okay, so a very common pattern. This is very easy code to write with the reactive APIs. This is much easier code to write than it would be if you're using non-reactive APIs. Can you imagine having to write this code? This is basically a deadlock. You're inducing a deadlock on purpose, a thread condition, a race condition. This is not easy code to write in the best of days, but especially if you have to do it over time across a large number of calls, it's a very tedious pattern to get right. This is not a message of hope, my friends. There's only one person who truly understands how to write safe, correct, multi-threaded Java code, and it doesn't matter who it is. It's not you. That's the important thing to remember here. It's not you. I don't know who it is. It's not you statistically. So use the framework. Let the runtime take the risk and do the work for you of making sure that you get the results you expect in the way that you expect it in a deterministic fashion, right? So we've got people that have worked on this for years and years and years, and the results are going to be better, I guarantee you, than what you're going to come up with, tonight, right? So this framework allows you to do things, to write robust service interactions and to, compose streams of data much more naturally. Hedging is one pattern, but there's all sorts of other use cases here, right? Imagine you have two different streams, A and B. One returns prices and the other one returns orders, okay? So you could say prices and orders, and then you'd get a stream back with a tuple with two elements in it, okay? Come on, tuple. And the tuple, you could say T1, and T2, etc. Okay, so that's one. That's a good idea. You can actually merge those things together at runtime. Good. Okay. Zipping is like a zipper. You take one from the left stream, one from the right stream, one from the left stream, one from the right, and then it's sort of interlocking pattern, and they get emitted on each new request. That's another thing. It's very easy to do using these reactive APIs. There's even, anything where you're doing scatter gather kinds of assembly of data is a very natural thing to do in a reactive API. There's even a third-party project. It has no relation to the Spring team. It's not an official Spring project, whatever, but it's just very interesting. It's called assembler. And assembler gives you the ability to describe a logical transaction. So it says transaction.class. There's no assembler type called transaction. It's just a logical one. Like it could be order, right? Your order, and then I want to create an assembler of order.class where I have line items and customers and so on. And customers are the correlation ID, right? So I create a rule that describes one-to-one billing info for customers, assuming billing info.customer matches the ID extractor, and then one-to-many as list, getting all the orders for customers, assuming it matches order item, customer ID, and etc. And so this actually does scatter gather calls. It launches a bunch of reactive streams at the same time, takes the results, aggregates them into a response, and sends them back to the client. Okay, so really, that sort of service composition use case is super, super interesting, especially as reactive programming is concerned. This is not stuff you would want to do without reactive APIs. It's just much more natural this way. So we have now a simple API adapter that just gives us a view of the downstream reservations. We've looked at a number of different patterns here. For want of time, I'm going to leave the discussion of a circuit breaker, which is sort of like a retry and an on-error resume and a timeout, all packed into one with a little bit more smarts for another episode, another installment. You can find my Spring tips video. It's actually just a few more lines of code, but I want to divert our attention now to the topic of RSocket. Okay, so the Spring Cloud Circuit Breaker abstraction, super powerful. It's in the code base online that I linked you to before, the Reactive Revolution. Let's turn to RSocket. Thus far, everything I've shown you has been in HTTP, and I like HTTP. I think it's got a future. It's going to go places one day. It's certainly a nice document retrieval protocol, but that said, I don't think it's a great service-to-service protocol. I don't think it is a great foundation for service-to-service communication. And I'm not alone in that fairly obvious conclusion, right? A lot of different organizations have arrived at the same conclusion as well. Google, for their part, created gRPC, right, which is a separate way of building services that goes beyond what HTTP can do. gRPC requires you to use Google protocol buffs, and it's based on HTTP2, which of course is pipelined, not multiplexed, but it's still a far sight better than HTTP1. That said, I still think we can do better, and I'm not alone. There's a number of engineers from Netflix who went to Facebook, and they created a protocol, binary protocol called RSocket. Now, RSocket is a reactive network protocol. It's a protocol that has back pressure as a first-class concept, as opposed to HTTP. Remember, HTTP does not understand reactive programming. At the protocol level, there's nothing in HTTP that I can use to translate back pressure, right? All that a reactive HTTP service can do when a HTTP client disconnects from that service is cancel the production of the data that was being used to serve the client. That's it. There's no way for the client to say, I want to request 10 more records, and then 2 days later, request 10 more, right? Again, there's no way to do that. All I can do is ask for the data or cancel the data. There's nothing in between. There's no requesting and, just requesting more and more and more and more. You can't do session resumption, put another way, okay? The other problem with HTTP, especially with HTTP1, is that it's stateless, right? It makes sense for scaling out a document retrieval network, but it's not great if you're trying to ensure as low latency as possible between service invocations. So if I want to make a call to an HTTP service, I have to make a network call, open up the connection, do the handshake, get the response, and then dismantle all that each time. Very inefficient. It would be much better if I could keep the connection open, if I could keep the socket open, and then just get new transactions on the same socket. I'd save all that setup and destruction cost. The reactive protocol, this RSocket protocol, is natively reactive on the wire, but it actually goes further than back pressure. It has kind of like reverse back pressure, right? So the RSocket protocol advertises information about the health of the service that the client can use to determine whether it's effective or it's useful to make a call to that service. So you might be familiar with this pattern, right? If you've ever used the Spring Boot actuator. Actuator is a module you can add to your Spring Boot applications. I used to talk about it a lot in my old cloud native Java talk. It's a set of management endpoints. It gives you things like the metrics, the uptime, the health, things that you can use to determine whether that service to which you're trying to make that request is healthy enough to respond in time, okay? Very, very convenient for smart load balancing use cases. That said, this is a Spring Bootism. It was inspired by a white paper from Google. And so hopefully between Spring Boot, which is, I suspect, the very large majority of people that have this pattern in practice, and the Google, the ex-Zooglers who are using that practice in their code bases, between those two communities, let's say there's a lot of people that have this pattern, but by no means can we consider this a convention or even a standard, right? This is not something that people are guaranteed to have for all their HTTP services. It's just something you kind of have to know about. Wouldn't it be nice if there was a guarantee that for every HTTP service that I make an API call to, there was some API I could hit to ask it how healthy it is, how much RAM it's got, how many users are visiting the system, what are the metrics, etc. This information is stuff that a client might want to know. Well, RSocket has a protocol frame specifically designed to carry this kind of information. So it's a natively reactive protocol. It's stateful, so you don't constantly have to set up the connection again. It supports all the different message exchange patterns you might expect to be able to have, which go a far side further than what you can do with HTTP, which only supports request response. So I can do fire and forget. I can do stream in, stream out. I can do single value in, stream out. I can do stream in and single value out. All the different kinds of back and forth in exchange patterns, message exchange patterns. And it's also payload agnostic. So it doesn't care if it's text or binary or whatever. It doesn't need to be Google protocol buffers. It doesn't need to be JSON or XML or anything. It can be whatever you want. And it has headers. I can't believe I have to say that in 2020, but it actually has headers, which WebSockets do not. Right? WebSockets on the wire in the WebSocket protocol have no concept of headers. It's up to you to use a second tier encoding, something like stomp, to provide as the payload of the WebSocket message a envelope object which has headers and a payload, and then that stomp envelope object you can then use to propagate out of band information like an access token, right, for security. But that's not built in by default. So if you want to use that in WebSockets, you have to agree on using WebSockets, you have to agree on stomp, and then you have to agree on the payload in the stomp message, which is 3 levels of indirection, right, between you and the actual contract of your service. So RSocket gets around that by just solving it the way it should have been solved in the first place. It has headers. So it's great for a lot of service use cases that you would probably find a lot of uses for. So what I'm going to do is I'm going to integrate an RSocket service into my reservation service. Now, I can do that because I have Spring Boot Starter RSocket on the class path. I can also do that because the Java client for building RSocket services, as developed by the folks from Netflix who went to Facebook, is using Project Reactor, not RxJava, Reactor, okay? And so it's trivial for us to then adapt that API. And we even took it one step further and built a programming model around it that looks fairly similar to some of the other APIs in Spring using message mapping. And that's it. That's my entire RSocket component. Here, I'm going to create an RSocket port. I'm going to run it in port 8888. Okay, so there's my RSocket service. On my client side, I'm going to create a RSocket requester. Now, this is kind of like a client, but consider that when an RSocket node connects with another node, there's no such thing as client service. Once they're connected, either side can initiate the discussion. Either side can send as much as it wants, whenever it wants, and so on. So it's they're considered requester responder. At any given exchange, one is making the request, one is responding, but they're not a client service. They're peer-to-peer, sort of. So here's my RSocket requester. And now I'm going to make one more API endpoint, API adapter endpoint called greetings name. Okay, new handler function, server response .ok.content type. Here I'm going to send back a server sent event stream. So I'm going to send back the body of the RSocket request. So I'll say RSocket requester. I'm going to inject that here. And I'll say RSocket.route, and the route is greetings, right? That's the endpoint there. The data that I'm going to send in is the new greetings request. And the data that I'm going to get, the name I'm going to send in is the name I'm going to get from the path variable. So server.path variable name, right? That's this curly bracket name, curly bracket business there. Name. The data I expect back is of type greetings response. And I'm just going to return the whole thing. So it's a stream of greetings. Greeting response. Good. 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 All right, there's my entire endpoint. Let's go ahead and restart that with 12 seconds to spare. Uh-oh. Oh, 77. Oh, it's 8888. Son of a gun. Look at that. Okay, try again. Happy, good. Curl, HTTP, localhost, 9999 / greetings / javaBin. Okay. So I'm making a network call across the wire. I have an HTTP server side event client representation here. I'm using that for my API, adapter. My edge service would connect to that server side event stream, so I could use a JavaScript client to talk to my the server side event stream, or I could use WebSockets instead. I could create a WebSocket endpoint. But that data is in turn being driven by a natively reactive RSocket stream across the wire. And that's making the call to the downstream greeting service. I'm getting back the response. I'm sending it back to the client. And there's not any glue code there. It's everything expects a publisher and everything produces a publisher. So these things just compose very naturally. All right, my friends, I hope that you got something out of this. I hope that you learned something. We've only begun to scratch the surface of what is possible here today. I know that there's a lot of things that you could be doing right now with your time. I hope you found this a worthy use of your time. And I hope that you appreciate that this is just the beginning. What I've shown you today is not just how to build applications that look and work as concisely, if not more, than what you've already got today, but I've shown you some possibilities that are reactive first. RSocket is not possible without reactive, right? Spring Cloud Gateway is a reactive first API, things like that. So things are, and some of the patterns that I showed you today are also not easy to do without reactive APIs. This is not just about reusing threads. It's about having a better programming model for building service composition and orchestration pipelines. Okay, so a lot of interesting possibilities here. I hope you'll also consider looking more into RSocket. It's a brand new protocol. We work with the engineers from Netflix and Facebook. We are fledgling members of the Reactive Foundation, along with a small company in China called Alibaba. They're going to be big one day. You watch that space. They're going to be big. The folks at Alibaba are kind of interesting, as are the folks from Netflix, right? These are people that are building, giga internet scale services, like web scale services. These services are all powered by Spring, right? Everything at Netflix is they standardize on Spring Boot as the de facto standard for services at Netflix, and ditto for Alibaba. Everything at Alibaba is based on Spring as well. And there's not just one Alibaba. Like Netflix is just one big company, right? It's a monolithic company with a lot of different microservices. Alibaba is a huge consortium of different companies, all of which are huge, right? And all of which have huge amounts of microservices, all of which are based on Spring. And so I spend a lot of time in China. I go to Hangzhou in China, which is where Alibaba's headquarters is. It's a couple hours away from Shanghai. And I spend a few days to a week every year just picking their brains. First, doing my best to help update them on what we're doing in the Spring community, and then also learning what they're doing with Spring to find out how we can optimize for certain use cases. So, in 2012, I went there and I started spreading the gospel around Java configuration, right? And then we talked about, back in 2014, I remember going to them and saying, hey, there's this thing called Spring Boot. You should really try it out. It's going to be a big one day. And then 2015, Spring Cloud, and then Reactive in 2016 and 17, and then suddenly RSocket in 2018, right? And so the folks there are using this stuff. They're adopting it in earnest, right? And they're doing amazing things with it. And so one of the things that has come out of this discussion and this fledgling Reactive Foundation, where RSocket now lives, is this idea of a broker. And the RSocket broker capabilities, I think, are very interesting. I've already showed you that we can very easily build services using RSocket, and I forgot to mention that you can also build RSocket services that are secured using Spring Security. That's easy. We have security support there as well. One of the really interesting possibilities is this idea of a broker. Imagine a broker that sits there and acts as sort of a gateway for your RSocket connections. The outside world sends requests to the broker, and the broker has open connections with all the downstream microservices that could possibly accommodate your particular request. It finds the one that's least busy by asking it using that metadata frame that we talked about earlier, and then forwards the request to the downstream service. That downstream service can either produce a response, or if it's too busy and if there's nothing available, the broker can respond with 100% back pressure saying, you're connected, but I'm not going to be able to give you anything. And that can be signaled. It can be communicated back to the client. So there's some very interesting possibilities there. But also consider that those downstream services to which the broker is forwarding those requests don't have to be open. They don't have to be. They don't have to accept any inbound requests. They can launch a connection to the broker when they start up, and they can have 100%, completely blocked ingress rules in their firewall. No ingress whatsoever. No inbound connections whatsoever, because they open up a connection to the broker, and that connection stays open, right? It's a stateful connection. So some really interesting possibilities once you have the broker. It can act as a service registry. It can help you do some of the things that you would otherwise use a queue for, like a Kafka or a RabbitMQ queue. Not all the use cases. If you want durable storage, then of course you're going to still want to use a Kafka or whatever. But if you want aggressive consumer, that kind of thing, work stealing, that kind of thing, then you can use a service registry. You can use a broker like this for. A lot of things become easier in the world of reactive APIs. That's all I'm trying to say. There's a lot of really interesting possibilities. So I hope you'll give it a go. I hope you'll feedback. I'm happy to answer questions now. I really appreciate your time. Talk, everybody. And by the way, stay safe. Some things should not be open sourced. Coronavirus is definitely one of them. I am, as always, Josh at joshlong.com and at StarbucksMan on Twitter.
Thank you so much, Josh.
Thank you.
And well done. Thank you so much for being with us this evening. I have
my pleasure, of course.
I have some questions from the audience.
Please, yeah.
Yeah, so let's start with the first one. The first one is, testing with reactive is difficult. What improvements have been made in that regard?
I don't know that that's true. I reject the assertion, but here's how that works. I should have, let me see if I can go back here. So here I am in my reservation service, and I've got a test, right? Regular old test. The way we encourage people to test, let's suppose I have a flux.just A, B, C, okay? So here's a reactive stream. We provide a step verifier. And the step verifier, you can pass in any publisher, and you can use that to assert things about the publisher. So I can say, I expect the next result to be A, B, C, and I can verify that that's true. Or I could do, I can say, expect next is going to be just A and B, and then expect the next count one more. So I'm going to say, I don't care what the third one is, but I'm expecting there's going to be a third one. Okay. So the step verifier allows you to assert things, and it takes care of making what is otherwise asynchronous and reactive look like a synchronous and deterministic thing. So you can just assert things in a deterministic way. So that's very useful. I also did a whole talk on this called Beautiful Testing. So look for the most recent editions of Beautiful testing or Beautiful space testing, and you'll find that I look at how to test services, microservices using Spring Cloud Contract, and so on, all in terms of reactive APIs. And there's also a web test client. There's a reactive web test client, so you can do testing of HTTP endpoints as well. I'll talk about that as well.
Yes, thank you. Let's see. There's another question. I will read it. How do we encapsulate blocking calls within Reactor, assuming it's inevitable? What is the best approach?
So I touched on that a little bit in the talk, but the idea is that you want to make sure you cordon that off, you isolate it, you put it on the appropriate blocking scheduler, right? You say subscribe on or publish on, and you give it a scheduler that's designed to create a new thread for every single request, as opposed to a non-blocking thread pool, which just keeps a very scant few number of threads and then just repurposes them, right? So that's more like in a traditional thread pool where you have to create a new thread each time you get a request up until a certain upper bound, right? That's the most important part. You can also adapt ignoring whether they're blocking or not. If you have APIs that aren't reactive, even if they're asynchronous, right? You can adapt them using a factory method like flux.create or flux.generate. These are great for taking things that are not reactive and then adapting them into your reactive world, right? So you can handle things like threading and spinning up a thread and all that stuff in that code, and then have that pump new events into a publisher, which then downstream things can consume like any old publisher.
I have a couple of questions from our community. The first one is stack traces. Is it difficult to infer why something failed if stuff happens on different threads?
Yeah, it can be, but so we have a few things that you can use. And actually, let me see, is it here? Spring Boot, enable. I haven't figured out how to do it in IntelliJ. They have a new thing here. So yeah, we have Reactor, debug, mode, IntelliJ, blah, blah, blah. See this, product Reactor. If you have Reactor in your project, there you go. Can you see that? You can't really see that, can you? There's a facility called Reactor Debug Mode, which actually it makes it so that you can see where things are failing in a particular assembly trace. So again, it's not a stack trace because errors in Reactor tend to be across multiple threads. So we give you the aggregate view of all that, and that's actually supported through a set of tools, right? That you can actually add to the class path. But if you're using IntelliJ, they've now taken that basic functionality that's already in Reactor, as a Java agent kind of. They've already taken that facility and now made it a view that you can get access to inside of the IDE. So the support has always been there inside of your Reactor APIs. It's just now there as well. I did a Spring Tips video, Spring Tips debugging reactive code. Here we go. I did this. Oh, look at that, May of last year. So we're getting close to the, well, I guess we're still a month and a half away from its anniversary. And the code, github.com, spring-tips. Okay. Debugging Reactor applications. And there's several things in here that you can just add to the class path, including the Reactor test support. We looked at block count, I talked to you about that, and Reactor tools. So you add Reactor tools to the class path. And then in your code, source, main, Java, debugger Reactive applications. In your code, you can use hooks on operator debug or Reactor debug agent, right? Hooks on operator debug is a way of adding things to a reactive assembly at runtime. It can be very inefficient. If you want that to be done at compile time, you can use the Reactor debug agent, or you can, and that works in addition to, or to the exclusion of, it works in addition to, not to the exclusion of block count as well. So there's those facilities as well. We also have a facility that lets you checkpoint. So you can actually write things. You can say, okay, I want to log this out at a certain point in the pipeline. I want to see what's happening, see what the state is, and so on. So there are facilities there to hopefully give you better visibility into what's happening when something fails.
Thank you.
Cheers. Thank you.
One last question.
Sure.
It's about Loom. The question is, if the goal is to handle as many requests as possible, then why choose reactive when one can actually continue coding without coordination, just by using fibers and virtual threads? What is your thoughts about that?
So that's just not true, right? Again, if the goal is to continue using input stream and you're using Loom, right? The problems with input stream.read are still there, right? There's a reason that Java has had asynchronous IO in the JDK since 2002, 18 years, right? It's because blocking IO is still problematic. So what we want is APIs that build on top of that, on top of asynchronous IO. So this is not just about threading. Like I said, I predicate the use of reactive on two things. One is, yes, getting better reuse of my threads, and two, having a better programming model that goes above and beyond synchronous and blocking IO, right? So reactive programming gives you both. By the way, Project Loom is a good first step, but what I really want to see is coroutines. So that'll be very interesting. Coroutines are the ability to say, coroutines are the ability to capture the behavior of the function or the behavior of the thread after something asynchronous has happened, and then resume that after I've finished executing this thing asynchronously, right? So Kotlin has this. Kotlin has a syntax sugar for this, but so do a bunch of other languages. Like Rust has async await support. C# originated the async await idea. JavaScript even has it. Python has it. So I would love to see that land in the JVM in Java itself. That support, it's basically syntax sugar for what Reactive is doing. If you're using coroutines from within Kotlin and you're using Spring, then we automatically support coroutines. So the Reactive APIs that you're using, everything you've just learned, is still valuable. In fact, it's foundational. You need to know it in order to understand what's happening when you use coroutines. But now when you write code using Kotlin, you get continuations. You get the ability to say, hey, do this thing on line 1, and then behind the scenes, it might actually suspend the thread. It might suspend the function and then disappear for a millisecond or nanosecond or a year. It's asynchronous, so you don't know. And then it'll come back and resume the execution of the thread. But even though it's doing that asynchronous thing behind the scenes and moving your work to a different thread, your code is written in such a way that it looks like it's just step 1, step 2, step 3, not step 1 dot then many, step 2 then many, step 3, right? You're not chaining stuff together. You're just writing this very deterministic, very sort of imperative style code might be more approachable for you. That's the real win. That's what I want, is to have Project Loom plus coroutines, as you can do in Kotlin. And there, your reactive APIs are made even better, right? Your reactive APIs now are, they give you better control flow and better scalability.
Super. Thank you so much, Josh.
Thank you.
Thank you so much from all of us in javaBin for being with us and contributing to our online meetups. We really appreciate it.
My pleasure.
I'm super happy to.
We're all in this together, my friends.
And to everyone that has been following our stream this evening, thank you so much for spending the time with us. And if there's any questions to Josh, please give him a follow on Twitter, and you probably can just reach out to him. If there's any questions about our community here in Norway, please reach out to us. You can find us on Twitter. And
it's a great community.
Thank you, Josh. And to everyone, stay safe, and thank you from us, and have a great evening. And with that said, I will end this session. So have a nice evening, everyone.